In a previous video, we investigated the system depicted here. That is, we have an object that is sliding back and forth sinusoidally along a straight line. In particular, what we did is we constructed the velocity vector as defined as the time derivative of the position vector. In this video, what I'd like to do is extend it just the next logical step forward. I'd like to construct the acceleration vector. The acceleration vector here defined as the time derivative of the velocity vector. So I'll start by providing a brief review of how we constructed this velocity vector, because we're going to take the exact same ideas and extend it to the acceleration vector. In particular, notice that we have the position vector at the current time t0 and at a future time t0 plus a delta t. So we had this, in addition to this one object right here, we also indicated that object slightly in the future, right? In this case, a time 0.4 seconds into that future. Next, we constructed position vectors for those 2 points right there. So here's the position vector for the current time, and there's the position vector for that time into the future. Now, in the numerator, we have the difference between those 2 position vectors. The difference between the 2 position vectors is this sort of pinkish purplish vector. That's the change in the position. But then what I need to do is take that change in position and divide it by a change in time, delta t. So that's this vector right here, this v right there. Notice that v points in the same direction as the dr, but it's divided by the delta t, in this case 0.4 seconds. Now what I'm going to do is stop this animation right here. I'll stop it right about there. This right here is my velocity vector. Actually, it's almost my velocity vector. It's the velocity vector before I take that limit t equals 0. So hold on with me. So I'm going to get rid of this difference in position vector, and I'm going to take the velocity vector here that I've calculated, and I'm going to bring it back up here. And then finally what I'm going to do is I'm going to implement that limit as delta t goes to 0. In other words, I'm going to look, instead of looking far into the future, I'm going to look closely into the future, right there. So in other words, take the limit as dt goes to 0. This isn't exactly all the way down there, but dt is small. It's 0.01 seconds. And lo and behold, this is the velocity vector right there for my object. It's the time derivative of this position vector in green. Let's let the time run again, and you can see it doing its thing. The velocity vector is aligned with the path when we're moving along a straight line. The velocity vector is large when this thing's moving quickly. It's small when it's moving slowly, and it's always pointing in the direction of motion. So now that we have a velocity vector, let's use the same ideas to construct an acceleration vector. I'm going to pause this thing right about here, maybe slightly into the future. And let's look and see what we have. The acceleration is the time derivative of velocity. So I'm going to need the velocity at some time in the future and subtract off from that the velocity at the current time. So let's go ahead and splay out our times again. So let's take the dt, and let's say look a half a second into the future. So we had points A right here, and then B was a half a second into the future. Right? This blue arrow right here is the velocity at the current time, the velocity for point A. What I need now is the velocity at point B. I want the velocity half a second into the future. So what I'm going to need to do is do the exact same construction that I did to get the velocity at point A. I'm going to need to do the same thing at point B, which means I'm going to need to look another half second into the future from point B. And that's what I call point C right here. So just as we did before, I'm going to construct a position vector for point C. Now to construct the velocity at point B here, what I need to do is take the difference between position vectors between point C and point B. That's going to be a vector going from B to C. And then I need to take that vector and divide by delta t, just as I did for point A. And when I do that construction without taking the limit as delta t goes to 0 yet, what I get is this vector right here, the one I have dashed. You can see the one that's dashed is bigger than the solid one. That is the delta r divided by delta t is bigger between B and C than it is between A and B. And you can see it here, right? Here's my current time at A. And what this is telling me, you can look at the points here. In the first half second after point A, I travel this much. And then the second half second, I travel even more. That's why this difference in position divided by time per unit time is bigger for that second half second. But of course, these are finite differences. These are time differences of half second. What I need to do is take that limit as delta t goes to 0. So when I take the limit as delta t goes to 0, look at those two vectors. They get closer and closer to each other. So there's the actual vectors. Here's the vector. The solid vector is the velocity vector at point A. And the dashed vector right next to it is the velocity vector at point B. These are the actual velocity vectors because I did take the limit as delta t goes to 0. And what I need to do is take the difference between those two vectors, which is very small, but I'm going to divide by delta t, which is also very small. And the result is, this vector right here, the red one, the A. There's my acceleration vector at this location in time. That's the construction. So what I'm going to do, just like I did before, I'm going to move this acceleration vector over to this object that's moving, like so. There's my acceleration vector, and let's watch it go. Let's run this thing forward in time. Wow. Alrighty, to finish up this video, I'd like to make a few observations. So first observation is that the velocity and acceleration vectors do not depend upon the choice of origin that we've made. Right? So here we put the origin up here. Why up here? I don't know. No reason to put it up there. I can put it anywhere I want. And we get the same behavior with these velocity and acceleration vectors. So really, the choice of origin is used to construct a position vector, but after that, everything else is a difference, so it doesn't matter where the origin is. Now, my second observation, and this is an important one, is that when the object is moving along a straight line, as it is here, then the velocity vector and the acceleration vector and the line itself, they're all collinear. They all lie along the same line. Now, it's important to know that this is only true if our motion is along a straight line. If we have a curvy path, all bets are off. This is not true anymore. But check it out. They all are collinear. For this next observation, I'm going to hide the acceleration vectors for a moment. And what I want you to do is notice when this thing's picking up speed, when it's slowing down, and when it's turning around. So there it goes. It's speeding up, it's slowing down, it's turning around. Speeding up, slowing down, turn around. And it's easiest to look at this stationary vector, I think, or this vector where the tail is stationary. When it's speeding up, that velocity vector is getting larger. When it's slowing down, it's getting smaller. When it turned around, it switched directions, right? Slowing down, speeding up, slowing down. There's a slowing down. Turned around, speeding up, slowing down, turned around. Say it with me. Speeding up, slowing down, turned around. Okay, now while it's doing this, let's look at those acceleration vectors. So here we're speeding up, now we're slowing down, And we just turned around, speeding up, slowing down, turned around. Notice that when we're speeding up, and we'll see it right, oops, let me find a place where I can pause this thing. When we're speeding up, like right here, the velocity and the acceleration are in the same direction, right? Do you notice that? When it's speeding up, they're in the same direction. Here we go, right here again, speeding up. And we'll do one more of these. So we'll pause this one right about here. So here it is, speeding up again. And it's almost easier to see why they're in the same direction when we spread apart the times again. This is kind of like what we saw earlier. So in that, when it's speeding up, over the first half a second here, it's going at some velocity. We see a change in position. And over that second half a second, the change in position is even bigger, right? That's when we get an acceleration to the right. That's when that dotted velocity is bigger than the solid velocity, and therefore the difference in those two velocities is also, in this case, downward and to the right. That's why they're all pointing in the same direction. Now what I want you to do is look at a case where it's slowing down. Right here it's speeding up, there it's slowing down, and this is probably a good place to look. Right? When it's slowing down, notice that the acceleration vector is in the opposite direction as the velocity. Right? Opposite direction. And again, we can explain it by splaying these times out, right? So in this first half second, we've got a big change in position. In the second half second, we've got a small change in position. The thing slowed down, and you can see it here, the two velocities. That first half second, that's the solid velocity vector, or at least average over that half second. And over that next half second, the average velocity vector is a lot smaller. So the difference between the dashed one and the solid one is a vector in the opposite direction of the velocity itself. Again, the observation here is that when we're in a state where the object is slowing down, like right here, the acceleration is in the opposite direction as velocity. We can see those all the time right here. It's slowing down right here. Yeah, speeding up in the same direction, slowing down in the opposite direction. All right, so now for this last observation, I want to turn off the acceleration vectors again. So accelerations are off. And what I want to do is I want to look at what happens when this thing turns around, right? There it is right there. It turns around. Let's do another one right about right here. Oops, a little too soon. Right here, it turned around. When it's turning around, at the moment it turns around, the velocity is momentarily zero, right? At that turnaround spot, the velocity is momentarily zero. Let's try to snag another one over here, right there. Oh, almost, so close. Right there. There's a good turnaround point. So here's my question. Remember, I hid the acceleration from you. At this turnaround point, what can you tell me about the acceleration? I'll pause for a second. What's the acceleration look like at this turnaround spot? Yeah? You thought about it? Pause if you need to, because we're going to talk about it. All right, at this turnaround point, a lot of students say, well, the velocity is zero at this point, right? And acceleration is the derivative of velocity. So the derivative of zero is zero, so the acceleration has to be zero. Makes sense, right? But wait a second, let me show you the accelerations again. Boom, boom. Oh, the accelerations are anything but zero right here. Totally not zero. The observations we're making here is that when velocity is zero momentarily, the acceleration generally is not zero. Yeah, why is the acceleration not zero when the velocity is zero? Let's look at this again. Let's watch this thing move with the accelerations on there. Yeah, where's the turnaround spot? Turnaround spot is, oops, I just missed it. Look for another turnaround spot. Turnaround spot's right there. Yeah, the acceleration is anything but 0. Right there. Here comes another turnaround spot right there. Oh, yeah. The acceleration is not 0 when the velocity is 0 because the velocity is only 0 for a split instant, right? The velocity is in the process of changing from being in one direction to going in the opposite direction. The velocity is not stationary there, right? The velocity is changing rather dramatically when it switches around, so the acceleration is definitely not 0 when that velocity is 0. All right, so that wraps up this video. I hope we learned something about velocity and acceleration.